Welcome to Tic-Tac-Toe the Hard Way, the podcast in which a writer and a software engineer train an AI to play a simple game.
And take a hands-on approach to exploring the very human choices that go into training a machine learning system.
And welcome back, everyone, to our machine learning adventure. And I think today we're actually going to start talking more about the learning bit. So good to see you, David.
Nice to see you.
Excellent, excellent. So remind us what you've done since we last talked.
I have generated many thousands of moves.
Moves.
This is data that we are going to train the system on. So each move consists of a string of 9 characters, each representing one box on the tic-tac-toe board with the marking where the X's and the O's are. I've also recorded who won the game, because all the moves come from games that have winners, and who the player is for this move.
Yeah.
And then the label, which for normal people, it's a weird use of label, but it's a label, which is what the next move will be, which is saved as the number of the box, the square in the grid.
Yeah. Perfect.
Okay.
Excellent. We have data. So now we can train things, right?
Yeah, we're practically finished. So how do you train something?
How do we train something?
How do you train a model?
Well, I guess to explain that, we actually have to explain what a model is. And we've been using that term occasionally. And I don't think we've talked about what that is.
We have not.
So I'm going to give a description of what a model is that's sort of geared towards a type of model you have made. And we'll sort of refine that. One way to think of a model, and I think a useful way to think of a model, is as a function that computes an output given an input. Does that make sense?
It makes sense.
So a function, you might think of that as a mathematical function if you have more of a math background. You might think of that as like a function in programming if you've done a bit of programming. Exactly that. It takes some inputs, and its job is to produce an output. In this case, the inputs are those board states, and its job is to produce that label, the move to make. Now, what's different about these kinds of models is that the internals of these models have some bits that can be changed. And those are the bits that we're going to change during the training process. So for example, we are going to take the board state in and we're going to do a series of mathematical operations. We're going to multiply some things, we're going to subtract some things, we're going to add some numbers to them in order to transform it into a representation that will lead to giving the right output. So that's going to happen inside that function, inside that model. The structure of that function is something we're going to give it as humans. You're going to actually code that up. But the specific numbers and relationships between things that it's going to do is something that it is going to learn. And there'll be an algorithm that we'll discuss in a bit that actually changes some of those dials inside the function in order to produce the correct output as it learns from examples. How does that sound?
I want a little more specificity, if you don't mind, because there are a million different sorts of models. It's a very common word. We use it in lots of different ways, from fashion and runway models and model planes and functions as well. So in a normal sort of computer function, if you're writing, say, JavaScript, as some of us are amateurs at, as you say, it takes an input, outputs something, and a typical function, sort of a dumb function, might be to square the number and divide by 2 or whatever, or look something up in a database and bring out the end. It's an input and then some type of computation that we understand, that we design, right? We specify how to do the math or how to do the database lookup. This model is going to be a neural network, an artificial neural network, right?
Yeah. Just to get on that point you made, the thing you described could be called a model, even if all of it is human specified. The difference here is that it's a learnable model. Therefore, there'll be something in there that the human doesn't specify. The human will specify certain things, but other things, it's just going to have to learn on its own. But to continue your point, yes, in this particular case, it's also going to be a neural network-based model.
Do you want to explain that? I don't think you want me explaining it.
I'll give a stab. And there's lots of things flying around on the internet that give illustrations and diagrams of neural networks. But one way to think of them is as a series of layers, each of which does some kind of computation and passes its output to the next layer. And you stack up those layers, and then if you stack them deep enough, you get deep learning. You stack up those layers, and that represents your function. Now, Each of those layers does a computation, and each of those layers has some learnable parameters, is what we call them. Those tunable dials are called parameters. So we're just going to stack up a bunch of those. Each one will pass its outputs to the next one. And down the chain, it will sort of learn something useful to give you the output at the end. The last layer is going to give us what number box to make the mark in.
So these neural networks famously can be very large and complex.
They can be.
Yeah, what we're doing won't be, right? It's tic-tac-toe, presumably.
You can make it arbitrarily complex, but yeah, we shouldn't make it overly complex.
Okay. The project is so low rent for that we shouldn't even be using
We
machine
are
learning for
in
it.
the baby steps of it. So it's a nice generalizable sort of system, but the specifics of the model structure, how many layers we'll use, we just don't need that many. But it sets us up as a nice baseline for your more complex problem.
Good. So I understand in normal programming, you write a function. Usually you give it a name internally, right? And it passes data and you specify what the transformations are and outcomes. This model will do the same thing. It's going to be doing it, and you're going to correct me as I get this wrong, right? In that we're going to pass in some data, it's going to have an output. It's going to yield that output by sending the data through a series of layers. I think the layers usually are talked about as consisting of nodes, each of which has some function, which maybe we'll talk about, but it does some type of transformation of the data that it's getting before it passes it along.
Yeah.
I think it's premature to talk about this, but in the training process, the weights get adjusted. Which no?
Yeah, you're correct. I only said that because we maybe haven't introduced terminology like weights, but that's often those numbers inside the layers or between layers can be referred to as weights. There's potentially lots of numbers inside a layer. Some are referred to as weights, some have other names. A general term for them is parameters. But all of those things can be adjusted.
Okay.
And the algorithm is free to adjust them in order to get better.
Okay, so that's models.
That's basically just what a model is. Now, how do we train it was the original question,
Yes.
right? So with the understanding that we basically have this function, but a lot of the parameters inside that function are, we don't know what the correct values are. So we have to find a way to get the correct values.
What makes a value correct?
Yes. What makes a value correct is that it gives you the right answer.
Aha.
It's very pragmatic.
Yeah.
Again, it does not care about a larger sense of truth or something. It's just what gives me the right answer is correct.
All right, so we're going to train it, or it's going to train itself in order to give answers that are right in the case of tic-tac-toe, in that they, as you would say, predict, or as I would say what the best move, a good move is for any particular board.
And specifically, it's going to train itself to match that data that you generated since we last spoke. So those labels, that's its notion of correct. Its job is to predict the same thing as those labels say, given the same input. Basically, you pass the numbers in, the model will make a prediction from where it starts off, and it's going to be wildly off the first time. But it's going to compare what it predicted with what you told it was the correct answer. And based on that, it's going to adjust all of its parameters and weights and so on to get closer to the correct answer. And if you just do this over and over again, and there's some details, you sort of do these in groups, you do this over and over again, and it gets closer and closer and closer to the right answer. And if you do it just right, and you sort of pick your parameters and everything right, it is able to predict the labels you give it across all of those examples. Because it really has to do this for all 10,000 plus boards that you're going to give it. So it's, while we're talking about it as if it's a one at a time thing, it has to do this well for all of those examples. And that's where some of the complexity comes into why these neural networks are structured the way they are.
Okay.
You sound ready.
Well, in some conceptually, maybe a little in terms of what it actually takes to do this. Nah.
If we step up a level, you feed it your inputs with labels, and it learns to predict the right label.
Okay, good. Good podcast. Thanks.
Excellent, yeah.
So giving it...
Luckily today, I'd say the details of that algorithm are something you never have to write. You actually do just give it the inputs and the labels, and all of that logic of how to adjust weights and everything, that's already been encapsulated and written up in these machine learning libraries.
So giving it means that somewhere there's a script or a program that as a very early step is going to open and read a file of data that I am providing. Am I right in assuming that providing it in the JSON format is an acceptable way of providing it?
You are right in assuming that is an acceptable way because you'll be writing the program that reads that JSON format. Now, there is something that you'll need to do in between because, like you said, you've recorded these board states as strings. Unfortunately, these machine learning models do not take strings. They really just understand numbers.
If I made it a string of numbers, would that do it? That would be very, very misleading.
A string of numbers is still a string.
Yeah, okay.
So we do have to find a way to just transform it into a format that sort of works for the machine learning model. And that process is one, you essentially sort of find a numerical representation for each element in your board, and you find a numerical representation for the move it should make.
Are we going to talk about one-hot arrays?
I don't know. Do you want to talk about one-hot arrays? Because you've done a little bit of this before.
I've done a little, yeah. It's a very weird concept. I'm afraid it will chew up the rest of this episode.
It depends how important you think it was. For example, your last foray into it. I'll give maybe a brief description.
Oh, I dare you. Go ahead.
So, for example, while I've said that these models can only take numbers, we want to be able to separate a number that's like a continuous number that grows from like 0 to 100 from just categories, where category 1 is not less than category 50. And one-hot arrays are a way to encode categories where you have a bunch of zeros in an array and you have a 1 in the slot for that category. So that's really all that is. It's just a way to use numbers to represent categories, but not have that issue of the natural ordering of numbers. That's it. It might be one of those things that's sort of best visualized in like some code or something, but that is one of the approaches we use to turn different kinds of things into numbers. We need to turn categories into numbers. We need to turn strings into numbers. True numbers, we can leave as numbers.
True numbers where they're not just standing for something like a square in a grid.
Exactly.
And we normally, humans, would number the 3x3 grid of tic-tac-toe. We'd put a 1 in the upper left and then a 2 and a 3 on the first row, et cetera.
Yeah. Or we'd call it top left corner and center.
Yes. But those numbers are completely arbitrary.
Exactly.
So you're going to have me write a program that's going to open up my data file, going to look at the data, which includes strings. It's going to turn the strings into these weird one-hot thingies, which don't imply any order. They're just good, clean data. Likewise, for the next move, the box that's going to be filled. And likewise, it will have the player.
The current player.
The current player who's making the move.
Who's making the move will also.
And who won the game that this move came from.
Now, I don't think that matters, but feel free to put it in.
Doesn't matter to me.
Again, we'll experiment.
Okay.
It's a great sort of perspective take is just to do an experiment and then do an experiment without it, because these should generally go pretty quickly. So you can do 2 experiments and see which one is better.
By the way, I just want to point out that the fact that training a machine learning model, even a small one like this, on a laptop is going to go really quickly. That's pretty amazing how far we've come. Okay. So I'm going to have all of, let's say it's 10,000 moves. I'm going to have those 10,000 collections of information, of data. Mm-hmm. What am I going to do with them?
So that's what you're actually going to feed into your model. You're going to also make a function that creates a model. And by that, I mean you're going to stack these layers on top of each other. So you're going to create that model, and then you're going to just feed your data into it. And when I say feed your data into, there's literally a function called fit that will do all of the work for you. You just pass it those 2 sets of arrays, or tensors, as you now know that they are called, and it will just do all of the work for you.
So there's a function called fit that I presume comes from a library, and I assume also it will be the TensorFlow.js library, which is an open source library, which is in fact developed by the group that we both work for.
Yeah, I work on that library.
Oh, do you? So you'll be able to answer some questions about it along the way, perhaps?
Yeah. I may have a vested interest in you being able to make this work. But I did want to sort of maybe ask you one question that's been implied by something I've said a few times when you've asked, like, oh, should I do X or Y? And I've just said, oh, just try it both ways and see. one thing we have to figure out is like, how do we know what's better, or how do we know it's working? Do you have a sense of ways you can know whether it's working or not, whether the training is working? Because you have a bit of past experience, but it would be nice to discuss how we know whether training is working.
So we're going to train it, and as it's training, the software can be set to show some outputs of the training. The aim is to train it on data where it knows the answer, it has the label, and see how accurate that output is compared to the ground truth of what it's been trained on. But also to test it on some input that it hasn't seen before and see how well it does with that.
Yeah, that's great. And the first form of that is what we typically call accuracy in this space. And the second, where we train it on unseen data, is something we might call validation accuracy, which is just validating the accuracy on a set that wasn't used for training.
So I assume what I'm going to do is I've got, let's say, 10,000 moves as my data. And I believe it's typical to set aside about 15% of that. So you train it on 85%.
Yeah.
And then test it on that 15 and see if it does as well or does well enough on that stuff it hasn't seen before.
Yeah, that's good rule of thumb.
Okay.
There's another approach which will also be useful in this scenario to know whether it's doing well, because those first metrics will tell you how well it's learning from that data. It won't exactly tell you how well it would perform in a competitive situation. So another thing you might want to do is take that agent and put it in that viewer environment that I've made and have it play against something. So currently we have a random agent, and that agent just plays random moves. So you want your agent to be able to also beat that in actual play. So accuracy is good. And then you want to see like, what is its win rate against a random agent? Because eventually we also want to know what its win rate is against my agent.
Oh, I think we know that.
Which will be the exciting bit.
I will crush you.
That's also what I expect.
Yeah, oh, for sure.
Grow in humility at that time.
So there's one big chunk that we actually skipped over, which is I am, but basically you, are going to set up the model that we're going to feed the data in order for it to train itself. What is involved in setting up? What does that mean?
Yeah, so setting up, it's sort of writing code that gives a configuration of what layers you're going to stack on top of each other. And the real art here is knowing what layers to stack on top of each other. And you can say that comes from a mixture of experience and best practice and intuition. So often I would say, and I'd advise anybody listening that's sort of trying to work on a problem, is find a similar problem that has already been solved and use that model structure and then adapt it to yours. As you grow in experience and intuition, you'll understand more of the reasons of why they picked that particular set of layers, and you'll be able to make those decisions independently. But before that point, just sort of reading what's in the literature as sort of best practice for given types of problems is a great place to start. Another thing I'd say is just to pick the simplest model that you can first and see how far it can go. When I say simplest model, it could be like 2 layers, could be like the simplest thing you can make. And you just make 2 layers and you maybe use some default configuration. And you don't have to know the right answer. You do that sort of iteratively.
So I understand that there's a pretty big set of knobs you can turn. What I think outside of machine learning we would call parameters, but I understand parameters is a term for something inside a model. So I think you call them hyperparameters.
Yeah, we call them hyperparameters.
So I understand there's a big bunch of knobs you can turn. But the basic decision seems to be, depends how basic, what you can count as basic, but how many layers, and then also what each layer does.
Yeah, so how many layers, the type of layer, and how wide that layer is, or how many parameters are in that layer. Those are sort of 3 big ones.
And just to sort of close out on models, and correct me when I'm wrong, the decisions that we make about the layers and what sort of functionality they ought to have, that will determine the common diagram of circles and nodes and just things connected, how wide the layer is. That will determine that sort of architecture.
Exactly. We'll sort of determine what the model looks like, the sort of shape or architecture, as you say, of the model.
But figuring out what goes on, I don't want to get into weights, but sort of
figure on the numbers in there.
Yeah.
That's what the training algorithm is going to do.
Okay.
So great. So do you have a good sense of what you're going to do next in order to train your model?
Yes, I'm going to be coming by your desk and asking for sample code and template and a million stupid questions. So this is the beginning of the...
Really, yeah, the beginning of the learning, both for the machine and for you. So
well, more for me. So
you'll learn together.
the machine is a blank slate. I'm worse than a blank slate.
You have some things to unlearn. Yeah, you have some things to unlearn.
Mainly
all of your
everything.
human biases. Awesome. Great. So I look forward to that and to figuring that out over the next few weeks. And we will catch up once you have a sort of agent playing and going that's learned from data.
I would not go that far.
I'm confident. I believe in you, David.
Thank you, Yannick.
All right, everyone. Until next time.
So long.
You've been listening to Tic-Tac-Toe the Hard Way with your hosts, Yannick and David Weinberger. This is a production of Google Pair, with thanks to Rebecca Salois, Eric Johansson, mixer and editor Brian Gordon,
and the entire Pair team of developers, researchers, designers, artists, philosophers, and more. A special thanks to Nikhil Thorat, who created the music with help from AI by Google Magenta.
You can find links to code and more in the show notes and at our website, pair.withgoogle.com/thehardway. Once again, that's pair.withgoogle.com/thehardway.